Well, we've seen that relativity affects a number of things, like whether events are simultaneous or not, and the length of things moving relative to you. It also slows down time. It also has an effect on mass. And to help us understand the effect on mass, we're going to work through this little animation here, a situation. Imagine two spacecraft out in deep space. There's three string lines, one strung up the middle, a top one and a bottom one. And when the spacecraft reach each of the lines, they've traveled a total distance of just 10 meters. In between them we have a bomb that's set to go off, and our bomb is going to explode. It's going to momentarily put a push on each spacecraft, and they are going to therefore travel at a constant velocity away from each other. And we know that 1 second has elapsed, they've reached their string lines, so they're moving with a velocity of 10 meters per second. Now what we do know is that they're going to agree that the green spacecraft will reach the top line when its clock has made one full revolution, and they're both going to agree that the blue spacecraft will reach the dotted line at the bottom when its clock has also done one full revolution, measuring 1 second in time. Okay, so let's think about momentum. We know that the law of conservation of momentum says the momentum before equals the momentum afterwards. Well, what was the momentum beforehand? The momentum beforehand was 0 before the bomb went off, and so therefore after the collision the momentum has to be 0. Well, how does that work? Because there definitely is some momentum. Well, it works because momentum is a vector quantity, and so the green spacecraft has some momentum upwards and the blue one has some momentum downwards. Okay, so in this situation here, momentum is conserved. Momentum is the mass times the velocity. Now, obviously these two spacecraft have exactly the same mass, and they've also got the same velocity, 10 meters per second up and 10 meters per second down. So all is well, everyone's happy, momentum is conserved. Now Einstein was really concerned to make sure that momentum has to always be conserved for frames of reference that are inertial frames of reference. Otherwise it too might become some way you could measure whether you're truly moving or not. So everyone has to see momentum conserved. Well, we're going to have a look at this situation now from this guy's point of view, the point of view of a guy in the green spacecraft. There's relative motion of 0.6 times the speed of light between them. Doesn't really matter which one's stationary and which one's moving, we don't know. There's just relative movement of 0.6 times the speed of light. They're moving left and right, okay? So the green one is whizzing one way and the blue one's whizzing the other way, and the bomb's going to go off just at the moment they pass each other. Well, in this case, I'm not going to try and model their X and Y motion because it would be incredibly fast. Remember, their vertical motion is only about 10 meters a second. So we're going to forget about their horizontal motion and just continue to look only at their vertical motion. Remember, these string lines are very, very long string lines, so you can easily measure your speed relative to the strings. Okay, remember what they agreed upon before. Well, let's set off the explosion, and we're going to agree that the green one's going to reach the top line when its clock has done one full revolution, and we're going to agree that the blue one is going to reach the bottom line when its clock has done a full revolution. But remember, this guy is going to see the blue clock running slow because there's 0.6 c relative motion between them. So he's going to realize that it's actually going to take longer for the blue spacecraft to reach its string line than it took for him to get to his. And in fact, the way that it works out at 0.6 times the speed of light, do the maths for yourself, it means that it's 1.25 seconds to travel the 10 meters, not 1 second, which means that the guy in the green spacecraft still believes he's moving upwards at 10 meters per second, but the guy in the blue spacecraft, from the green guy's point of view, is moving downwards only at 8 meters per second. Well, that's a real problem because it would mean that momentum is not conserved. There's going to be more upwards momentum than downwards momentum. And because momentum is mass times velocity, the only thing we've really got to work with here is mass. And so therefore the mass of the blue one compared to the observer in the green one, the mass of the blue spacecraft has to increase. So the mass of this spacecraft has to be a little bit more to make up for the fact that it's moving at a slower velocity. And so mass, in order to make sure that momentum is conserved, mass has to dilate or has to increase as you approach relative speeds close to the speed of light. And that is what mass dilation is. It's merely that the closer we get to the speed of light, the mass of a spacecraft tends to increase.